Okay. I'm going to talk about this paper that deals with the estimation of the non-Gaussian dimension that I call, or the number of non-Gaussian shocks in structural linear systems. Let me start by the motivation of my paper. It's like basically in mainstream microeconometrics, identification of the structural VRs resort on external restrictions. You can impose zeros, you can impose linear, non-linear sign restrictions, or you can use instruments or proxy variables. But all of this is external information. But there is identification strategy that I can label as the statistical identification of these models that has been proposed in the literature recently, that needs these two requirements. First, the independency, serial and mutual among components of the structural shocks, and the second assumption is the non-Gaussianity of each structural shocks. Why is this important? Because especially the second requirement, because it allows the researcher to exploit higher order information. You can exploit the third order moments, fourth order moments for identification purposes, so for obtaining more identification conditions, if you want. And the main advantage of this statistical identification, the strategy over the standard identification of structural bars, of structural bars, MAs, is that if your model is fundamental, then you can identify the static component without using any kind of external information or external restriction. And if you dealing with non-fundamental models, basically you also can identify the location of the roots. And the third one is that all the empirical hypotheses in terms of restrictions, they can be tested. So the crucial assumption is to determine how what's the amount of non-Gaussian shocks in the system, because that number, that dimension, is the one that is going to determine if your model is going to be identified or not. Regarding the related literature, I can relate it to these important papers in the literature, which is the paper of Lobato and Velasco, which basically is applying a Harke-Vera test, but is quite robust to higher order dependence or control for the correlation in the univariate series. Well, you can this paper can be seen as an extension or to a multivariate constants, and the other one that is very close related is the paper of Guy. He has a basically same setup as mine, but restricted to a causal structural vector autoregression, and he exploits the contemporaneous and third fourth order cumulants for identification, but also he develops a test for finding or an estimation procedure for determining the non-Gaussian dimension. Well, in fact, the contribution of this paper is that the method I propose is doesn't need this restriction of causal structural of causality or invertibility of the structural model. So the outline of my presentation, the outline of the presentation is going to be, I'm going to discuss the model and assumption, then I'm going to give you what is the relation between the cumulants and the non-Gaussian dimension, and then I will discuss the estimation of approach of this non-Gaussian dimension, and then I will show you some results. Well, the model that I have, I'm working is this structural vector autoregressive moving average model that can be represented here in this equation. Here you have an autoregressive polynomial and a moving average polynomial in which we only discard the presence of unit roots. The static component is represented by this full rank time invariant matrix, and you can see that within this setup, the setup of Guy is a case in which the moving average part is an identity matrix, and the roots of the autoregressive polynomial are restricted to be outside the unit circle. In my case, it's quite it's more general. And well, regarding the structural shocks in my systems, I'm assuming that they are IED sequence. They are also mutually independent among them. So, for instance, this means that imagine that you have inflation, you have GDP, and you have interest rate. So basically, what I'm saying is that the cost shock is not is independent from the demand shock and dependent from the monetary policy shock. That's what I'm assuming. I'm having the standard assumption regarding the moments of the structural shocks, but I'm requiring the finite 8 order moments because basically I'm gonna explode third and fourth order cumulants for the estimation, and then it's necessary double for inference. And I'm gonna here the number of non-Gaussian shocks in my system is of course between 0 and the total dimension of the the system. So basically here I'm not imposing how many non-Gaussian shocks are in this model. For instance, if this number of non-Gaussian shocks were smaller or equal than d minus 2, then the structural model is not identified. And if this is larger or equal than d minus 1, the structural model could be identified if and only if we impose the fundamentalness. So basically, we can identify a model, the static part of the model, but we need to restrict that these autoregressive or these dynamic polynomials, the roots needs to lie outside the unit circle. And we need that all of them must be non-Gaussian if we want the full identification, the dynamic, the location of the root, and also the static components. So this is why we cannot just to estimate structural shock, believing that this is fundamental or not, because basically what we are going to find is that the reduced form errors, they are possibly a linear combination of the current, the past, and the future values of the structural shocks. Okay, so of course you can think that okay, I can estimate the structural model believing that all are Gaussian, and then well you can do that. You can test if there is all of them are non-Gaussian. Of course, if there is one non-Gaussian, of course you are going to reject. But the problem is that if you want to advance to determine if there is one or two, yeah, then this problem, it makes like you will have one non-Gaussian shocks, but probably this non-Gaussianity it could transmit it to the whole system, and you could obtain that the whole there are two or more than one non-Gaussian shocks when this is not true. So that's the problem that you cannot I mean you can estimate, but then your inference is going to be probably is going to be inconsistent if you estimate this. So that's why we focus only on the reduced form errors, and the form of these residuals is, as I said, is a linear combination of the structural shocks, past, current, and future values. So now let me before going to the main result of my paper, let me explain how I characterize the the non-Gaussianity is through the cumulants. So basically, this is characterizing the non-Gaussianity by its higher order moments. I'm going to focus in this paper in third and fourth order cumulants, basically skewness and kurtosis coefficients. So when we impose the independence of the shocks, so serial independence and marginal independence, well, the structure of the vector that collects all the cumulants of order k has a very particular structure, which is given by this matrix. Okay, so basically what I'm saying with this is that when you have serial independence and mutual independence of the components, then all the non-marginal cumulants are going to be zero, and only the marginal cumulants could be different from zero. And then this is going to be the particular structure of this vector of cumulants. So you can see here, basically, that the rank of this matrix, V, is exactly the number of marginal cumulants different from zero. So you can use this for determining the non-Gaussian dimension, as you can see here. Well, this is the approach that has been studied by Maxam. Maxam setup is basically the same as Guy. It's a causal structural vector autoregression. She estimates the structural models without knowing the number of non-Gaussian shocks. She has a result that's saying that in this case, even though you have the possibility that the model is not identified, well, but the block or the non-Gaussian block is still or remain identified, while the Gaussian block is not identified. That's why she estimated the structural model, obtain the structural residuals, and basically try to test this, try to obtain the fourth order cumulants, the kurtosis of each shock, and estimate if this shock exhibit an excess kurtosis or no, and test this. And then she determines this. But as I have here, this cannot be done in this general setup. Why? Because here the matrix of cumulants of contemporaneous cumulants for the reduced form errors, okay, these are this is the summation of these matrices, which is then the rank of this matrix is not anymore related to the number of skewed or shocks with excess of kurtosis. So it's not related anymore to the non-Gaussian shock. This is why I use the spectral cumulant densities following Brindler. Well, this is the spectral cumulant density of the reduced form errors. And I can relate this spectral cumulant density with the cumulant density or the cumulants of the structural shock. And this is the relation that we have. Well, after just this is a vector similar to this vector. Okay, this is kind of this, but this is with the frequency. And I can reorder this in this matrix, and then I take the squared if you want. So this is going to be my matrix of interest, and if you can see here that since we are here we are neglecting, or we are assuming that there is no unit roots, then these objects are full rank in the unit circle, as well as the reduced form bar, because the reduced form bar is a fundamental bar map. So then this term is full rank in the unit circle. This is full rank in the unit circle. Then the rank of this matrix is related to this vector, and this is just a quadratic form, and which the rank of this quadratic form is related to the non-Gaussian dimension, the number of non-Gaussian shocks in the systems. So that's the proposition, or the main result of my paper. So when you use third order, the third spectral density, or also the big spectrum, then you are going to find the number, the non-Gaussian dimension spanned by shocks that are asymmetric. If you use the four-order spectral density, or also the tree spectrum, you are going to find the non-Gaussian dimension spanned by these shocks that has excess of kurtosis. And you can use both the third and fourth order cumulant spectral density. Then you can find what I call the non-Gaussian dimension, which is spanned by both asymmetric and or excessive kurtosis shocks. Okay, and the good thing is that, or the particularity of the result, that this also is valid even though the root or the locations are known. So imagine that the true model is fundamental. Well, this result applies the same. Okay, so this works for both when the location of root are known or unknown. Okay, so my estimation approach is going to be through a sequential test. Okay, I'm going to use in the paper. I use the claiming and pub approach because, as I explained, then my problem is to estimate the rank of a matrix, and that is going to give me the rank of or the number of non-Gaussian shocks or the non-Gaussian dimensions. And also here I run some exercise with the Robin and Smith test. Okay, but also since I'm not going to use the structural shock or the structural model, I cannot estimate these elements parametrically. So, however, this part that is using the reduced form errors, so this part I'm going to estimate this element non-parametrically. Yes, so this is going to introduce for the asymptotics. This introduce just a new element in the rate of convergences because it's necessary to introduce a smoothing. Okay, but that's the only peculiarity in terms of the asymptotics. But also, I'm not going to use the asymptotic test specifically because it's quite difficult to use this, because if you are testing the first or the joint normality, the first stage of my sequential procedure, then the critical values must be tabulated because the asymptotic distribution is not a chi-square, but it's a combination of the square of a chi-squares. And when we have mixed case in which you are testing one non-Gaussian against two or more, then the asymptotic distribution is a chi-square, but the problem is that the Gibbs freedoms are unknown. And well, that's why I prefer to use a bootstrap test. Besides, sorry, I haven't put this here. Besides, if you want to use the asymptotic approach, you need to calculate the asymptotic variance, especially in the case of the claiming and pub, and that the asymptotic variance of this of the estimation of these elements is quite difficult. Using analytically or asymptotically. So that's why I use a bootstrap approach for calculating for performing the test. Well, but this is also has some challenge, because the problem is, because the main challenge is that our bootstrap sample must reflect the null hypothesis. That's the recommendation of many papers, specifically in Portland and Dalem. So what we are going to do is follow the non-Gaussian approach. What we are going to take advantage is that we are going to use the vectors, the characteristic vectors associated to the singular or the smallest singular values of our matrix of interest, because these are going to be under the null. These characteristic vectors are or span the Gaussian dimension. So, but we are going to use this vector for constructing a matrix for span or for projecting the non-Gaussian dimension or the non-Gaussian space of our shocks. We are going to use this, and then for each null hypothesis, we are complete the Gaussian part with just a random draw for a multivariate standard normal distribution. If you want to see the details of this bootstrap sample, I can give you. If not, I can continue.
Miguel, can we also pass your allocated time? Can you please summarize in a couple of minutes?
Perfect. So I performed one simulation study and empirical application. My simulation study is quite simple. I'm going to simulate a 2 bivariate non-causal structural bar with these characteristics. And when I obtained this is the rejection rate using the claiming and unpub statistics. So what you have here in square boxes is the size of the test for each case. So we can see here that well, the size in the case of young Gaussianity is close to the level, to the chosen level. In the case of one Gaussian shock and one non-Gaussian shock, yeah, we have a little bit of excess of rejection. And in the case of two non-Gaussian shocks in this case, well, this represents the power, which this means that it's easier to reject the first, but it's more complicated to reject the once we advance in the sequence. Well, we have more results, more with higher sample size. Also, I've done I've used the Robin and Smith statistic. The main advantage of this statistic is that it's quite faster, much faster than the claiming and unpub approach. And when I apply to these two very famous data sets in macroeconometrics, I detect potentially one skew or asymmetric non-Gaussian shock. Okay, when I use kurtosis, I cannot detect any non-Gaussian shock. I believe that this is because the sample size is quite small, because here the sample size is 148 observations. Try to estimate a four order cumulants. It's quite complicated with this. When I apply this to Blanchard-Perotti, I basically can identify two skewed or potentially three shocks with excess of kurtosis. What is implied that I can apply the statistical identification strategy to these data sets. In the case of Blanchard-Qua, if I believe that the model is fundamental, I can apply this because it's necessary only in this case because you have D2, you need at least one if you impose the location in root. In this case, I can apply the statistical identification approach even without imposing the location of the roots. So many thanks for your attention. I'm sorry for exceeding my time.
Okay, thank you. No worries. We understand, especially the last two theoretical papers, you need more time to set down your assumptions. That's great. We don't expect in 20 minutes to learn everything about your work, but I think it was great, at least to see what you're doing. In many cases, I realized my personal comment before finishing here, so let me stop recording.